In this video, I'd like to go through the process of diagonalizing a matrix using this particular matrix. And you'll notice that this matrix has an interesting property where its transpose is equal to itself. And this is known as a symmetric matrix, and it's one of the special types of matrices that has certain properties that can make computations more efficiency, as we'll see throughout this example. So to diagonalize a matrix, recall that you first have to find the eigenvalues of the matrix. And we do that by solving for the eigenvalues from this equation. The determinant of A minus lambda times the identity matrix has to be equal to 0. And for this particular matrix, the determinant looks like this. I won't go through the details of calculating this determinant. I'll skip a few steps that you should find something like this. All right, and we can simplify this further in this form. And this has to equal to 0. This is a 4. So from here, we can immediately read off the eigenvalues for this matrix. One of the eigenvalues is lambda is equal to 4 because that makes this factor equal to 0. And then we have eigenvalues that are degenerate, so they're repeated. So the second and third eigenvalues are both equal to -2 because this factor is raised to the power of 2. So this is a case where we have degenerate eigenvalues. And you'll see that when we try to find 3 linearly independent eigenvectors to check if our original matrix is diagonalizable, we're going to have to be a bit more careful because we no longer have 3 distinct eigenvalues. So we'll start by finding the eigenvector for the distinct eigenvalue. Because it's easier. Once again, we do that by solving this system of equations. So it's basically this, but you substitute the value of lambda is equal to 1 over here. And this will give you the following matrix. And we'll denote the elements of our eigenvector as just x, y, and z. And this has to equal to the 0 vector. So from this system of equations, we get 2 equations that we need to satisfy. The first one is 3x minus 3z has to equal to 0. And the second one is 6y has to equal to 0. From this equation, we know that y has to equal to 0 because it's the only way to satisfy this condition. And from here, we again have the case of infinitely many solutions, but you see that when x and z are equal to 1, this condition is also satisfied. So we can say x has to equal to z, and we'll set that equal to 1 for simplicity. So that means that our first eigenvector will be given by 1, 0, 1. The norm of this vector is given by the square root of 2. So that means that our normalized eigenvector is this one over here. All right, so that's our first eigenvector. For our other two eigenvalues, so we'll begin by finding the second eigenvector by solving this system of equations. And this gives us the following matrix. And this is our eigenvector. And this has to equal to the 0 vector. Okay, so this gives us two redundant equations. Both of these equations over here are telling us the same thing, namely that 3x plus 3z has to equal to 0. And again, there's a variety of values for x and z that can satisfy this. We're going to choose x is equal to -1 and z is equal to 1. You could have also chosen x is equal to 1 and z is equal to -1, and you will get the same thing. This gives us a second eigenvector. It looks like that. The norm of this eigenvector is again square root of 2, giving us a normalized eigenvector that looks something like this. Right. Now for the third eigenvector, we don't have a third distinct eigenvalue. And if you remember from the last video, in order to be able to diagonalize our matrix, we need to find a third linearly independent eigenvector. That is linearly independent, which I'll write as Li, from our first two eigenvectors. And you have to be a bit more clever in constructing a third eigenvector in general. In this case, you'll notice that we didn't have any conditions on what the value of y was from these equations. So if you were to solve this system of equations for the third one, you will get the same matrix as above because the eigenvalue was the same. All right, so you have conditions for x and y that we use to construct the second eigenvector, but there's nothing telling you what the value of y can be. And what that means is that we're free to take any value of y that we want, and this equation will still be satisfied. So we can construct our third eigenvector from this information. So since there are no constraints on y, we are free to choose a value for y and still satisfy the system of equations. So this gives us our third eigenvector, where we're going to choose a value of y is equal to 1 for simplicity. And because the norm of this eigenvector is 1, this is also equal to the normalized eigenvector. And what you'll notice, just tangentially, is if you take the dot product of any two of these eigenvectors, you get, so if you take the dot product of the same eigenvectors, you get 1, which just tells you that they're normalized. And if you take the dot product of two distinct eigenvectors, you get 0, which tells you that they're orthogonal. And this is a general property of symmetric matrices. So for symmetric matrices, the eigenvectors, if they can be diagonalized, the eigenvectors are what are known as orthonormal. So they're both normalized and orthogonal to one another. So now that we have our three normalized eigenvectors, we can construct our matrix C. This looks something like that. So this is our first eigenvector. This is our second eigenvector. And this is the third eigenvector. And another interesting property of symmetric matrices that's useful for computation . So for symmetric matrices, the matrix that's built out of its eigenvectors is an orthogonal matrix. So what this means is the inverse of this matrix is equal to its transpose. So it makes the calculation of the inverse of this matrix very simple. So if this was our original matrix, all right, so since the inverse of this matrix has to be equal to the transpose because it's an orthogonal matrix, this means the inverse. So all of the elements along the diagonal remain the same. This element now comes over here. This one goes over here. This one goes over there. And this one comes over here. These two switch place. And you're left with the following matrix. And you should verify that if you were to carry out this computation, you will get the following diagonal matrix with the eigenvalues along the diagonal. All right. So in this video, you saw how using the properties of certain special matrices, we can make computations more efficient. And we went through the diagonalization process of a matrix. In the next video, we'll do a second example of a different class of matrices known as Hermitian matrices, which are important in quantum mechanics.